Good morning, everybody.
Hey Bryce, I'm excited to listen to you talk.
Good. I'm glad you're here. It's already been a morning, y'all. I'm gonna get started in just a second because I only have 40 minutes. But my wife had a doctor's appointment, and our 3-year-old woke up sick this morning, and so he's being bribed in the other room right now with cookies to be quiet for the next 35 to 40 minutes. So we're gonna cross our fingers. So let's see. Count down. It's 10 a.m. I'm gonna go ahead and get started because, like I said, we only have the 40 minutes, and it is a lot going on this morning. So I'm trying to figure out how to share my screen. Let's see. Thank you all for coming. Today I'm going to be talking about explainable data fusion. Can y'all see my presentation screen?
Yes, we can.
Okay, all right, perfect, because that's on the front. So whether you're here to learn about explainable data fusion or you just need your seminar credit, I'm glad you made it. So we're going to go ahead and get started. Today I'm going to be talking about explainable data fusion. Let me actually record this too. I'm sorry. Oh, cool. Sorry. Okay, so today I'm going to talk about explainable data fusion and what that means and what we're doing with it and where we're going from there. So first, I'm going to start off with a little bit about me. My name is Bryce Murray. I am originally from a little town in Mississippi called Natchez, down on the river. I graduated high school and got my undergrad in computer science, physics, and math from a little college right outside of Jackson called Mississippi College. From there, I went to Mississippi State University, where I participated in a handful of different projects under Dr. Anderson, which is how I ended up at Mizzou. And this is our group right here. There's originally only 2 of us that came up from Mississippi, but you can see we kind of expanded. And shout out to all you guys that are actually out there in the crowd. Miss seeing your faces in the lab, and hopefully it'll be soon when we get back in there. But what we actually came to talk about today, and that's going to be explainable data fusion. So one of the first questions I'm going to start off with is going to be, what is explainable artificial intelligence? We're seeing it kind of all over the place. It's popping up in the news as people are wanting a little bit more, I guess, trustworthiness out of their artificial intelligence. As it's starting to kind of hit different sectors, we're starting to realize that a lot of the solutions that are coming out now are more black box solutions. We don't really understand why they're coming up with the decisions or the outputs that they're coming up with. And so there's this kind of like this movement towards explainability in our systems. And so what is explainability? And so really, I guess you have to answer the question of what is AI, but we're going to take a step back and kind of look at how some of these pieces kind of tie together. And one of the first ones is the data. We have data from different sources. If you're here, there's a good chance that you are working with some type of data, and so that's not a new concept to you, but we can get it from all over the place. And that is one of the first areas that we can kind of start to build a little bit of explainability, or that's the approach that I've taken with the data fusion. But then the next place is actually going to be the AI. Is it going to be a neural network? Is it going to be some type of genetic algorithm? Is it going to be some type of fuzzy inference system or fusion, like we'll be talking about today? And so all these different types of algorithms that kind of fall under the blanket of AI, they're also going to be a means of explainability, whether we'll talk about, I'm getting a little ahead of myself, but it's going to be some type of explainability that can be formed there. And so whenever you kind of combine these two things, we get the model that's being built by the AI from the data. And that's the third place that we can kind of have this concept of an explanation from AI. Also, I know I'm a fast talker, so I apologize. I start talking too fast, somebody chime in and slow me down. But one of the things that we really are getting at the heart at with explainability is going to be answering a handful of questions that kind of prod what we hope that explainability is. These originally came from a DARPA paper a few years ago, but they kind of form a good foundational set of questions of what are we looking for when we actually have an explanation. And so as we dig in, we're really going to be asking, why did you do that? Why not something else? When are you going to succeed? When do you fail? When can I trust you? And how can I correct an error? Which I've made this joke before, but those are the exact set of questions that I've asked the 3-year-old right before I came in here, so that he would stay quiet while we're in here. And they're not, it's probably just as easy to ask the AI those questions as a 3-year-old who really can't understand what's going on and doesn't have a notion of, I really don't know why I did that. I don't know why I just made that decision. Why my convolutional neural network said that this was a cat. Why I decided to leave all the toys out in the middle of the floor, just because that's just what I did. And so as the AIs have gotten more sophisticated, explainability has kind of taken form. And so this is just a handful of the words that really come into play whenever we're talking about explainability. Each one of these words means something slightly different. And one of the ones that is a little comical maybe is that one of the words for explainable AI is actually explainable. And so some of these things are actually a little circular in their definitions. Whenever you start talking about certain ones of these words, the other words actually pop up in their definitions. And so it really kind of had me digging in, but two of the ones, actually, let's go with, two of the ones that have kind of taken more meaning to me, I guess, are going to be the transparent and interpretable. Interpretable actually is going to mean we understand how the inputs map to the outputs. So whenever you get something in and we get an answer out, can we mathematically represent what's actually going on? And then transparency is going to be, can we get the AI at some level to tell us what's going on so that we can understand and maybe kind of probe a little bit of what's happening in an AI. And then let's see, what is an explanation? And so this is going to be another hot topic, is how you actually transfer this information over to a human. And so if you've worked with neural networks, you've probably seen some type of deconvolution or something of that nature where they're trying to highlight what areas of a filter are actually firing on an image. But one of the questions is, what is actually the representation when we're talking about these different things? And so is it just going to be raw statistics? Is it going to be some type of visualization? Or is it going to be some type of language? Is it going to be a summary that says, hey, this is what the AI did and this is why it did it? But maybe it's going to be some form of all three. Those are more of kind of the questions with where the explainable community actually is right now. And more works are kind of coming out every day that kind of hit on each one of these things. I was reading one yesterday about responsibility in AI, which is another sector altogether. But it's point being, it's kind of a transforming field, and it's kind of a moving target, because as each new work comes out with explainability, it kind of shifts the mindset in a new direction to a certain degree. So that's kind of it on the explainability. That kind of sets a stage of, okay, what type of explainability are we building into data fusion so that we actually still fit into the category of explainable AI? So as we move forward, the first question I'm going to answer is, what is fusion? That way we can have a basis of what's actually going on and why it's necessary. So two of the more common approaches may be like a multi-sensor fusion, where you're going to be fusing information from different sources, sensors. And this is a picture I Googled. I did not come up with this, but it was a pretty interesting one, because even if you look at the legend down here, this hits a variety of 5 different sensors, and then all around the car there's sensors that are being used for different reasons. And so one of the things that's important is going to be, can you actually fuse the sources to actually get an algorithm that is going to be doing what you want it to do. One of the other popular ones is actually going to be the multi-algorithm fusion, or multi, we'll just leave it at that. And so if you have a KNN classifier or support vector machine, or any of the, I guess I'll call them older school types of algorithms are doing classification, or if you even come to today and you have the deep learners, which is one of the things that we've used, is going to be a handful of the more sophisticated deep learners on a classification task. And so in both of these scenarios, we're wanting to fuse things. And the question is, one, how do we fuse? And then two, what actually happened in the fusion? Is it explainable? Is there something that happened that we can actually understand? And so as we go to the next slide, it's going to be, what is explainable fusion? So I've been working on this for a handful of years, starting, I guess, really in the first publication was 2018, but I think we can actually track it back a little bit further than that. And so I am standing kind of on the shoulders of fusion giants when it comes to some of these works, because they have, some of these authors have worked on these things for a while. They've worked with optimizing the fusion and different things like that. And I'm kind of stepping in after the models are already learned, to figure out how do we actually break down explanations from these different topics. So this is just a handful of the ones. If you're interested in any of those publications, shoot me an email after it's over, and I'll make sure that you have a copy. So this is this is going to be the fusion operation. And so one of the things that I have a hard time doing is is being able to articulate at a high level exactly what's going on. We could get down, we could talk about the capacity that represents the measure that's happening and all these different things that are going on under the hood. But at a high level, this is how we represent the fusion, which is going to be specifically the Choquet integral. And so each one of these bubbles is going to represent a different layer of fusion, or a different parameter that's in the fusion solution. So as we start at the bottom, we have, let me step back, we have three sources, x1, x2, and x3. And as we come into the lattice, we start at the bottom and we aggregate on our way up. So in this node, we have a parameter that is going to represent the weight that is going to be applied to when we fuse x1 and x2, and then x1, x2, x3. We start at the bottom, we can take any number of walks going up this, and a walk is going to actually be determined by the sort of the sources. So if x1 is the largest, we're going to start here. If x2 is the largest, we'll start here. If x3 is the largest, we'll start here. And then we'll work our way up until we're to the top of the lattice. I'm going to go through another example in just a second, but basically I just wanted to give you a kind of a quick overview of what the Choquet integral is and how we're going to be representing it for the next 22 minutes. So the question is how do we define each one of those little bubbles in the parameter, which are the parameters? And so first we have data, and as that data comes in, we're actually going to sort that data so that it is in the right format. And then after we do that, we're going to learn the measure. There is so many different ways to learn this measure. But what's unique about this XAI is it's not specific to any type of learning algorithm. It doesn't really care about that. It really only cares about, one, it's going to care about the data, and then two, about the measure that was actually learned, or the parameters in the fusion solution. And so then it actually learns each one of the parameters that exist here in these nodes. So you may have put this together from just a second ago, but each different walk up the lattice is actually going to be a different linear convex sum. And so we're going to call each sum a walk today, and that's kind of what we've termed it. And that's, again, going to be how we step up the lattice. I know I keep hitting that point a little hard, but a lot of the XAI, or the explainable data fusion of today, this presentation is going to be built around, one, this sort, and then two, how these parameters are operating. And here's a little, I guess, a little nugget of knowledge. That is also going to be exactly how the Choquet integral is going to be naturally interpretable. We can directly map our inputs to our output whenever it comes up. So that's one kind of checkbox for how we're going to work and kind of exploit the natural interpretability of the Choquet integral. And so this was an example whenever we go x1, x1, x3, and then x1, x2, x3, if we receive the data in that order. But here's where we introduce the problem. What happens whenever we don't have enough data to actually cover all of the sorts? That means that whenever we're learning these parameters, there are gaps that we didn't understand, or we didn't have data to support it. And so that's really one of the properties that I'm going to be exploiting with the XAI, is how do we actually account for this in, one, some of the traditional methods to understand the sources, and then two, what does that tell us about our model? Are we able to actually come back and, quantify how much of our model was supported, or how many walks are missing? And the answer is going to be yes to both of those, but we're going to get exactly how in just a second. So now we're going to kind of get into what is explainable AI for the Choquet integral. And so in the publications I showed you just a second ago, there's a handful of different new indices that I've put together and are going to actually highlight what's going on in the Choquet integral, which, if you're paying attention, that's going to be something that's going to help us to achieve transparency in the model. And so we've gone from interpretability, and you kind of see a progression into transparency as we knock out some of these different indices. So the first set says, can we highlight model specific XAI? So that's going to be, once we've learned the parameters and the bubbles and the lattice, what does that tell us? And then one, can we highlight data specific XAI? So just looking at the data, we know that the data has to be sorted, which tells us which parameters are touched. And if we know which parameters are touched or supported by the data, then we can learn something about how well our model is set up. And then the potential variability index, which maybe is my favorite, but it actually is going to tell you if you're missing a parameter in your model and we're given a new source, how much, what is the coverage of the data relative to the new source? So if you're missing one of those bubbles in the lattice, what contribution could it have made versus what we actually gave it? Because we didn't have data to support that, but it was defined kind of a default value based on whichever learning algorithm you chose. And so I'm going to say it's going to be a little bit harder to trust because we have a range. And so I'll get into that in just a second. But it's pretty interesting. And I jumped ahead. So, all right. So for the very first indices or index that we have, it's going to be the Shapley index. And the Shapley index is one that actually models the contribution of each one of your sources. So how important was source 1? How important was source 2? How important was source 3? If we're fusing deep learners for classification, how important was GoogleNet compared to CafeNet, compared to InceptionNet? And this is going to be able to tell us what those relative contributions are. The Shapley index is not anything new. It's been around for a while. What is new is going to be my algorithm that goes in and removes from the Shapley calculation the contribution of these parameters that are missing. So for just a second, let's assume that the black circles contain source 1 and the red circles don't. And so if we're looking for the contribution of source 1, we're basically looking at how well are these, what are these bubbles relative contribution versus the red ones? Well, that's not a problem to calculate. It's been done before with this part of this equation. I'm assuming you can see my mouse. But the question that I raised was, well, we don't see all the data, so how do we accurately reflect that in the Shapley calculation? So what I've done is gone through and added this indicator function and then renormalized to make sure that some properties still hold. But essentially what that's doing is that's throwing these bubbles out. And so now that these bubbles are thrown out, we can actually have an idea of the contribution of each source relative to the data supported variables. So I'll say that one more time just to kind of like hit home with that. And that's going to be, we only use values that are data supported to make this calculation for source contribution. That's important because before, if we use all the variables, we're going to be biased by whichever learning algorithm you choose, because it's going to fill in these values whether they're data supported or not. So what does that mean in an example? So you can go check out the paper, but basically, if you calculate the typical Shapley, we can have this situation where we go from these values. This one's worth 0.68, 0.18, 0.13. They're going to sum to 1. But then whenever you actually come down here, we have the case where you can actually switch the order of importance. So in this case, source 2 was the second most important, but here it's actually the least important, by a pretty good shift. And so that kind of highlights like how or why this index is actually important. So there's another one. There's actually called the interaction index, and it's going to be very similar to the Shapley, except instead of modeling source contribution, it models how two sources interact. And so are they redundant? Are they complementary? And that's kind of what they're going to be doing. And so what this equation does is essentially the exact same thing, but what it's going to do is it's going to model those values similarly, and this is just another example of kind of how that works. And so similar to the Shapley, I added an indicator function, which seems like a simple contribution, but it actually turns out to be extremely applicable in these different situations. And it took a little bit of work to figure out how to go about actually finding these parameters and basically zeroing them out. And this slide got a little out of order, so I apologize for that. So that was the model-specific XAI that talks about the contribution of the sources, but now we're going to look at the data supportedness. And the first one we're going to actually come to is the walk visitation index. So this is going to say, we've seen the lattice, but how observed is each walk? And so in this case, we have the case where these two bubbles might not have been seen. And so this is going to be some data that actually reflects this lattice, where the yellow dots were supported by data, the clear ones were not. And so this is the number of possible sorts. These are the sorts that we actually might have encountered during data. And so what actually happens is that we don't see these bubbles because we go 1, 2, 3, 1, 3, 2, and then 2, 1, 3. And so these 5 were encountered, but these were not. And so what we actually do is we compute these were seen 1/3 of the time because we had 3 data points. And then whenever we saw those, they were seen each 1/3 of the time, where the rest of the sorter would have been given a 0. So ideally, these would all be the same value because we would have equal coverage of each of the walks. But we know just from looking at the data and real world examples, that's not realistic. So because we're dealing in a realistic world, that's again why part of this work has come about. So lastly is going to be the potential variability index. And so in this case, looks like I'm running a little short on time. The rest of this, I'm only going to walk through one example. But assuming that we get to sort x2, x1, x3, that's going to be x2, x1, x3, we have a potential variability of 0 because we see every single variable. But whenever we have x1, x2, x3, this is a problem. We are walking over a variable that did not have data to support it. So the range that this value could take on is going to be anywhere from 0.1 to 1. And so that's going to be 0.9. So that's going to be a pretty large value of uncertainty that's kind of associated with this value. And so what we do is we're going to multiply that by what the input values are, and that's going to give us our potential variability index. So that's going to allow us to account for kind of a range of values that this could have taken on to give us some kind of notion on how much you can trust. May not be the best word, but for the sake of this argument, I'm going to use the word trust. How much you can trust a new input when it's coming in. If that value is high, then that means that it could have covered a large range because we just didn't have data to support it. But on the flip side, if it's low, then we have data to support it. So we have this kind of notion of trust a little bit more in the variables or the walks that come in to the integral that are actually cover, walks that we've seen. So that kind of wraps up. Oh no, sorry, it doesn't. We applied this to a image classification problem with fusing these 7 neural networks. I'm sure everybody is familiar with neural networks at this point in time. We did it to several different data sets. I'm going to show the AID data set. It is a remote sensing data set that has 10,000 images with 30 classes. The specifics on how this was actually done can be found in the paper, or if you have any questions, let me know. But for the sake of brevity, we're going to look at the results. And so one of the things that we looked at is going to be the Shapley index. And so as you can see, these are the Shapley index spit out for each one of the networks. And for the most, or for some cases, they did stay in the same order, but in all bottom 3, they did not, to some degree. Some of them, remain relative in their position, but what we really see is we see a big jump on some of them, as much as 5 to 6%, even in class 30, with a pretty drastic change with the ordering. And so that just really goes to show that the walk-centric Shapley, which is the one that I presented, that I extended, is not just a little more applicable, but can be extremely more practical whenever applying it in a real-world scenario. And then over on this side, it's a lot of numbers, but what we're actually going to be looking at is going to be the frequency of the top walk. So whenever you take the walk visitation index, you can see that in this real-world data set, it would cover usually 35 to 40% of the walks with that same ordering. And so what that's telling us about the deep learners is they are consistently making kind of the same order whenever they're predicting what the class should be. And then if you look at the top 2 walks, it's as much as 80% right here, as little as 56%, but I mean, that's still a lot. And so whenever you're looking at the 80%, what that's saying is we saw the same 2 walks 80% of the time. We can almost, account for those 2 walks setting up what most of the integral is going to be, because we just don't have very diverse coverage, which can be a problem. It takes a little bit more like digging into to see, is that actually a problem? But it really kind of points in the direction of, if you're having a fusion problem with this setup, this might be the first place, or this would be one of the first places that will look. So that kind of wraps that up. And so, but as you can see, even from this one slide, this is a lot of numbers. And we really didn't even show you but 2 different indices. Whenever you start talking about the other 6 that come into play, it's just so much information that it's kind of information overload. And so whenever we're talking about explainability, this one is going to hit on the statistics. There's too many statistics for, I would make the argument for really anyone to digest, but more so anyone that's not familiar with this particular fusion solution. And so we saw the gap there. So the next thing that I've actually done is going to produce this next paper, which is going to be fusion to text. So we're taking these different these different indices and then condensing them down into a set of summaries. That way we can effectively represent in a short manner all of the insights that can be generated from the fusion, from the explainability on the fusion. So we have this data, we produce the fusion from data-driven fusion, but then we extract the low-level XAI, and then we need to generate insights so that person can actually figure out what's going on. So the main questions are going to be, how are we fusing? Are there training implications? How can we extract the XAI, which we pretty much just covered? And then we're going to be talking about how can we bridge the gap from low level to the high level XAI, why and how are linguistic protoform summaries used, and then how is it going to be useful in practice? And we're going to apply it to the classification problem. So way too much data. In this case, whenever the classification, I didn't have much time to touch on this, but for each class, there's a separate integral. And so that leaves us with 30 different Shoke integrals, 30 different fusion solutions, 30 different sets of XAI indices. 30 different sets of XAI indices, which is a ton of information. So I showed you on that last slide in the last part of the talk where we had all those statistics for just one. So now you multiply it times 30 and you can really see the problem of all of these mini raw values and how we're going to bridge the gap to come down to just a few summaries. So I'm going to step away from the fusion for just a second. We're going to talk about protoforms. So what is a linguistic protoform? I didn't know much about them before like jumping into this paper, but they turned out to be pretty cool and pretty practical. And so the simple protoform is going to be of the form QY's RP, where Q is going to be our quantifier, and so most, many, some, or few. Y is going to be our object. In this case, it's going to be the sources, the network, or the walks, and the summarizer, important, observed. So most sources are important. Few sources are important. Few walks are observed. And so you can kind of see how this would translate our statistic up to a higher level that really anybody can understand. And so one of the things that you have to do, though, is whenever we're looking at the quantifier and the summarizer, those are going to be fuzzy sets that kind of represent the space for those words. So for the summarizers, for everything in this case, I've chosen the trapezoidal membership function. If you have questions about that, we can talk about that too later. But that is going to be what is most often used for the linguistic protoform summary community, and it tends to work pretty well. But the question came in was, how do you actually choose these values? And so basically, I considered a source important if its Shapley value was going to be at least 1/7, because we know that the Shapley values are going to sum to 1. We have 7 sources, so we want it to be at 1/7. Similarly for observed, 1/7 factorial is going to be how many possible walks there are. And I have 10 minutes left. Okay, so that's how that was chosen. But for the quantifier, we also have to do the fuzzy sets. And so I can talk about this later, or if you have any questions, but those are also kind of chosen. And the same with the walk visitation quantifier. I can rationalize all of those and how they were chosen, and they are in the paper, so I can send you that too. But the question is going to be, how is this useful in practice? And so what we've actually done, or what has been done, is going to be we've taken the walk visitation, so 30 times, this is just a big number, and this is a lot of statistics that we can read. Not enough time of the day to go through, or a couple of days. But what we can do is funnel these down, and when we produce these summaries, we actually end up with 42, which is a lot more digestible. I mean, you can almost fit that on a one-page PDF. But this is why these summaries are going to be trackable. So, and I've even condensed it down a little bit further into a graphic. That way you can really just look at one picture and figure out what is happening. So the question is going to be, how many sources are important? And so this is what we actually produced with the land classification on the AID data set using the 7 deep learners. And what we would hope to see is this chart over here. So in this case, we had many sources are important, few sources are important, several sources are important. What we want is most sources are important, but you can see that we never actually saw that. Most of the time, only several sources are important, which goes to show like, hey, not all your sources are important. But then the question is going to be, what do you want to do with that? And so one of the things you can do is you can just throw out the sources that aren't worth anything. Maybe it costs too much to run those extra 3 deep learners. Maybe you want to figure out how to make those 3 deep learners that aren't doing very well step up their game and go back and retrain them until they're, a little bit more in line with what the other ones are doing. If you can explain a deep learner, but that's another topic altogether. So whenever we get into the another way to kind of highlight these deep learners are to see how often which ones are important. So across the 30 different classes, few ResNets, are important. And so one of the things that's associated with the linguistic pluriform summary is a truth degree, which kind of, the idea behind this is kind of give a relevance factor. So if I was to say it's cold outside and it's really, I don't know how cold it is outside, it's 50 degrees. That's obviously not quite as, it gives you a little bit of context, I guess, is to say, y'all are probably in Missouri. I don't know, I'm assuming. And you kind of have an idea of to what degree it is true when I say it's cold outside. And so whenever we're looking at the truth degrees, a high truth degree is going to be a little bit more absolute. We completely believe that few ResNets are important. And so you can see in this gap in the middle that that's not always the case, which just kind of goes to show that like these are probably borderline between most and several, or most and most or most. And so, but the two best deep learners in this case that this highlighted were actually going to be InceptionNet and ExceptionNet. So the next set of insights was actually going to be the number of walks. And so this is going to be the walk ordering 1 through 7, and then, there's not really much variation. But for this set of summaries, there are going to be, over 150,000 possible walks, but there were only 5 that had a truth degree of 1. So only these 5 walks are observed. And so we can get into why exactly we see 1, 2, 3, 4 over and over again, but that's a little bit beyond the scope of this. So lastly, the fusion to text takeaways are going to be the data-driven optimization produces way too many values to understand effectively, and we've generated summaries that kind of highlight exactly how we can take this information up to a high level so that a non-Shoki integral expert can hopefully understand, digest, and use what we have learned through the explainable aspect of the data fusion. So I know I kind of hit all of that really quickly, and I only have 5 minutes left. Are there any questions?
Hey, Bryce, I had a question. So the techniques you discussed obviously are really specific to the Shoki integral, which is useful for me since I also have to deal with that quite a bit. But do you think, as like a big grandiose question, do you ever foresee there being like a unifying theory of explainability, or do you think it's going to have to be pretty model specific as it is currently?
I would like there to be a kind of, what you're kind of describing is going to be a model agnostic. So is there going to be explainability that extends beyond, the Shoki integral, beyond a deep learner, beyond whatever? And there are some methods that are heading towards model agnostic, but I think that the problem with that is that you can really only probe the black box and figure out what's going to come out of it. I think that those are going to start to kind of like hit a plateau. This is all my opinion, so feel free to argue. What I think that we're going to start to see more of, and we're already starting to see, is kind of explainability by design. Can we bring explainability into the picture, into the questions whenever we're starting to build these things? And how do we factor that into the performance? Because obviously, like, there's probably a graph somewhere that says as explainability goes up, performance goes down, and we don't want that. We want, both of them to stay high. So what I think is going to happen, and my 3-year-old is walking in the room, I think what's going to happen is we're going to see the explainability start to get built in on the front side so that we can build the performance, or that it won't come at the cost of the performance, if that kind of gets at your question.
Yeah, that makes sense.
But I could talk for a couple of hours on that, so.
Hey, Bryce.
Yes, what you got, Alex?
So those indices we just saw a few slides earlier, are these indices of the networks?
Say that one more time, you came across a little muffled.
Oh yeah, so a few slides back, there are indices of yeah, that one. No. Yeah, the one after. One more.
One after, okay.
Yeah. So are these indices of the networks?
These are the sort order that was, yes, yeah. So this is what came out of the network. So network 1, 2, 3, 4, 5, and 6 is just their confidence values per class.
Oh, okay. So would this kind of technique applicable to say if we want to dive deeper into the feature channels, would that be applicable?
How do you want to dive deeper into the feature channels? Are you saying going back to dive into the neural networks?
Yeah. So what if if I want to check if just some of the channels are important, just like a different.
So that's what Shapely value is going to be doing. So if you go back to this one, so this might, don't quote me on this, I don't know what order these ones correspond to on these networks, but this could be let's say 1, 2, 3, 4, 5, 6, 7. And so what that's actually going to tell you is which networks or which features are the most important. Does that get your question?
Yeah, absolutely. Thanks.
Yeah, so that's also why the interaction index is cool too, because say that your Google nets are complementary or redundant with, the inception net, then that might tell you, are these kind of queuing in on the same features, or are they doing opposite features? It might, I have to think about this, but kind of represent some type of diversity in the learning. I don't know if they're redundant. I don't know. All right, I've got less than a minute left, and I have no control over that. So I'm going to thank you all for coming. If you have any more questions, feel free to email me and reach out. So yeah, thanks y'all.
Thanks, Bryce.